Hi everyone, I'm happy to welcome you to our third Power Rectifier webinar session. Today's topic is the secret of efficient and compact clip-flat power packages. And first of all, again, I would like to introduce today's presenters to you. Basically, we are in the same team constellation as for the first two Rectifier webinars. My name is Ole Thomsen. I'm working as a product manager for Nexperia. And we have Nima Lotfi in the call. Nima is our product application engineer, and basically he did all the lab experiments for today's session. And last but not least, we have Hoan in the call, and Hoan is part of our development engineering team. So let's have a look on today's agenda, and we will switch off our camera. So today's agenda, first of all, I would like to wrap up the first and the second webinar session briefly before we will dive into today's topic. Therefore, I will introduce some prominent power rectifier packages before Hoan will explain the concept of the thermal resistance, and he will also explain some thermal principles. Then in section 4, Nima will take over and do the thermal benchmarking of SMx versus CFP packages before I will shed some light on the quality benchmarking with respect to board level reliability testing, also SMx packages compared to CFP packages. And in chapter 6, we will summarize the whole webinar before we will open the Q&A session. So let's start with the recap session. So the first webinar covered rectifier principles. Therefore, we have, first of all, introduced a very generic PN junction on an atomic level. We've explained the construction and also how the exchange of charge carriers looks like. Then we have introduced the rectifier portfolio. We've seen that different atomic structures were leading to different diode characteristics. And then we've taken a characteristical IV curve, and on that we have explained the most relevant and also mainly static data sheet parameters. So for instance, we have explained the forward voltage drop VF and also the reverse leakage currents IR. And with that, we have taken a reverse polarity protection application and benchmarked various rectifiers with respect to efficiency in that specific application. And the second webinar covered rectifiers in switching applications. We have taken a simplified cross-section of a planar and a trench Schottky rectifier and explained why a trench is beneficial in switching applications. Then we have explained the reverse recovery effect, and also we've shown why the reverse recovery charge is the essential parameter for switching loss. On the basis of a basic switching cell consisting of a transistor, an inductor, and a diode, we have benchmarked different rectifiers, and we did efficiency breakdown analysis with a 48 to 12 volt DC-DC buck converter. And all these sessions have been recorded, and in case you've missed one of the sessions, you can find the recording also on YouTube. So with that, let's dive into today's topic. First of all, I would like to introduce some prominent power rectifier packages. And in general, the package has the function to house the silicon die and also to protect the die from the environment. And furthermore, also the package should transfer the generated heat from the die as good as possible into the PCB. And therefore, you can see some different types here shown. So let's start with the wire bonded SMD packages. I have indicated here two examples, a D pack and a D square pack. And these are SMD packages, and they do have a wire bond inside. Usually the forward current rating of these products starts with the D pack from 3, 4, 5 amps and then going up to 10 or 15 amps. And the square pack can be considered as the bigger brother of the D-pack, and the forward current rating is between 10 and 30 or even 40 amps. Then on the right side, we have the wire bonded through-hole packages. The construction of the package is pretty similar. The big difference is that you have these leads which can be plugged through the PCB. And for instance, the TO220 does also house dies with a forward current rating between 10 and 30 amps, and then the TO247 starts from 30 and goes up to 60, 75, or even higher forward current ratings. But today's focus is on the clip-bonded SMD packages, and the wording CFP is an Xperia wording, and it stands for clip-bonded flat power. And here you can see an overview of the package we would like to cover in today's webinar. And for the thermal benchmarking in Nima's section, we have decided to choose the CFP2 HP, the CFP3, and an SMA package. And the reason for that is that these are the most relevant package for the forward current rating of 1 amp. So theoretically, you could find the same silicon die inside all of these packages. And for the thermal benchmarking, it was very important to have the same technology and also the same die size in the packages. And in the quality benchmarking, we decided to fall back on the larger CFP packages. Therefore, we have used the CFP5 and 15B and the SMA-BC packages. And with that, on the next slide, I would like to explain briefly the advantages of the copper clip. So first of all, the image on the top left reveals also the inside of the product. And you can see in the gray color, the silicon die, which is sandwiched between the clip and the lead frame. And the advantages the clip has is, first of all, that you have a much better connection from the die compared to a wire bond, because simply the coverage is much larger and better. And this also enables much higher pulse handling capabilities of clip bonded products compared to wire bonded products. And now in the following image, you can see a comparison of the 3 cross sections of an SMA against a CFP3 and a CFP2 HP package. And here you can also find the silicon die in blue color, which has the same size for all the 3 products. The clip connects the die now with the lead frame. And with respect to PCB saving on the right, you can see that if you start from an SMA package, you can save up to 75% of PCB space when moving from an SMA package to a CFP2 HP package. On the next slide, you can see all the packages displayed again, and it clearly can be seen that the HP package has this exposed heat sink. So HP stands for high power, and the comparison of the recommended footprint is coming here on the next image. First the CFP2 HP, and then an overlap image of the CFP3 on top. And finally, the SMA package overlapped. And now we have identified the occupied PCB area and put it in contrast. So the SMA for sure is the biggest package. It has 13.5 square millimeters of occupied PCB area, whereas the CFP2 HP only has 3.9 square millimeters. And now also a very important factor with respect to the heat dissipation is the occupied pad area, because this is the area which really transfers the heat into the PCB. And here you can see that the SMA for sure has also the biggest pad area. So the anode and the cathode tab have been summed up, and it results in 5.7 square millimeters compared to 2.55 for the CFP2 HP. And yeah, it's clearly visible, it's a big difference. But if we take the ratio between these 2 areas, you can see that 65% of the whole area is covered with the heatsink for the CFP2 HP, whereas the CFP3 and the SMA only have a coverage of 42%. And now a very important question which we would like to answer in the following is how can CFP packages compensate the much smaller pad area? And with that, I would like to hand over to Hoan.
Okay, so thank you, Ole. I will try to explain the basic RTH concept and some thermal basics to understand really the question Ole raised. So before we really come to RTH, we need to understand why is really RTH a key parameter to define device performance. And for this, we can just have a look at the data sheet we supply. And one limiting parameter for the device performance is really the junction temperature, the maximum junction temperature the device should have. The TJ listed here with 175 degrees. I mean, this is the temperature, yeah, the diode can operate until it's, so to say, destroyed. And another important parameter you see already here in this data sheet is the total power dissipation, the PTOD, right? So this is the value how much power the device can handle, can dissipate. And indeed, those two values, the temperature and the total power dissipation, is linked via the RTH. And in the data sheet, you will find two different kinds of RTH values, the RTH junction to ambient and the RTH junction to solar point. We will later learn what is the difference between those, but as of right now, just keep in mind that the RTH junction to ambient is dependent on device and the PCB layout. And the RTH junction to solar point is a device-specific parameter independent of PCB and surrounding. And if we have a look now at the formula shown here, we can now see the relation between the temperature, the junction temperature, and the RTH and the total dissipated power. And you can already see from this simple formula that indeed, if you want to maximize the dissipated power we can draw from the device, we need to optimize the RTH value. Or in other words, or looking at the different angle of this formula, how is the maximum ambient temperature we can apply to the device in order not to surpass the maximum temperature of the junction. And indeed, also this simple view is determined by the RTH value. In this case, the RTH value junction to ambient. From this very simple view, we can already see that RTH value is a very important device performance parameter. And now let's dive in more detail why we define different kinds of RTH values. For that, what is in general RTH junction to ambient or junction to solar point means? So RTH R, X, Y means that we use two different reference points, X and Y. We measure the temperature difference between those reference points and divided the temperature difference by the power dissipated along this path, X and Y. So effectively means, for instance, RTH junction to ambient means that we measure the junction as one reference point and the ambient as a second reference point. So to understand this in more detail, we now show here a cross-sectional view of one of our clip-bonded packages. You see in the center the die, you see the clip connected to the top of the die, and the die is sitting on the lead frame, which is then also connected to the PCB. So in the simple picture, the die itself dissipates power. And from this simple picture, you can see that we have two different routes for the heat to dissipate in the clip-on packages. One route is through the clip. So here we would call this route, or we would link this to an RTH clip to solder point. And the other route you see here is to the bottom of the die, so to say, through the lead frame, then to the solar point. That's what we would call RTH junction to solar point. And important is, this junction to solar point is really just dependent on the device, on the device design, on the clip design itself. So nothing to do with the PCB, because as of right now, we didn't consider the inference of the PCB. So basically, if we have a look at the RTH junction to solder point, this is a very device-specific parameter. If we go further, if we want to go to the ambient, we need to consider that the device itself is connected to the ambient via a PCB. And indeed, by continuing this path, we will see that also we have a connection from the solder point to the PCB, then from the PCB to ambient. And until then, we have the total picture for the RTH. And indeed, if we want to sum up all the inferences and we want to see how is the junction to ambient RTH, we need to sum all these pieces: RTH junction to solder point to PCB, and PCB to ambient. So we learn now here is that the value RTH junction to ambient is the overall thermal resistance of the system, including the solder joints of the package to the PCB and the PCB itself. We will see later in Nima's part that really we can manipulate this RTH junction to ambient by improving the PCB thermal resistance. I already talked a lot about thermal resistance, and indeed this term is chosen because similar to the electric domain, you can also draw a electric circuit diagram for thermal components. And indeed, the thermal resistance is similar behaving to electrical resistance in the electric domain. And see in this table here, there are similar thermal components or parameters which can be linked to electrical components in the electrical domain. And what you can now see is, if we do so, on the right-hand side of this slide, you can see an equivalent circuit diagram of one of the devices. And indeed, you can now draw the total power dissipation as, so to say, a source. We measure the temperature difference, similar, which we would measure electrical potential. And now you can attribute each component of the device with a certain resistance. So the die has a resistance, and follow this, we have a parallel path of a die clip and a lead frame, as I already mentioned. The device itself is soldered onto the PCB, and then from here we would measure the temperature difference between the ambient and solder point, and then we would have a resistance from the PCB. In parallel to all that, we have minor contributions of radiation and convection. And with this equivalent circuit diagram, we can now really see why this packages Ole already showed have differences in terms of RTH. I mentioned earlier, RTH junction to solder point is device specific, and if we now have a more closer look into the device shown by this cross section, you see that each of these packages have different kinds of clip designs, lead frame designs. For instance, the SMA package has a very large clip path, so to say, so it takes a long path to get out of the system. And also the lead frame has a long path. The CFP3 instead is very compact, and the path outside, so to say, of the package is very small. And in addition to that, the CFP2HB, as already mentioned, has an exposed heatsink. That means that any heat generated by the die is directly transferred, so to say, vertically down to the PCB. And that's the reason why all these different kinds of packages have different kinds of RTH junction to solder point. And this becomes very clear if we now take again the occupied PCB area, which is already shown by Ole. And now we also put in this table the RTH junction to ambient values and the RTH junction to solder point values. You see for the junction to ambient value, which here in that case is just given by on top of the standard footprint, you will see that the SMA package has the best or the smallest RTH junction to ambient value. But if we just take a look at junction to solar point, so the device-specific resistance, we see that CFP2HP has the best thermal performance. And we will later see that as soon as we increase the PCB design, in that case, that we increase the heat dissipation out of the PCB, we see that we can draw the most of the CFP2HP package. Before I come to an end, let me quickly also hint to another parameter which is similar to the electric domain, and this is called the dynamic thermal impedance. So similar to electrical impedance, as soon as you have pulse applications, so something dynamical, you also have to introduce the so-called thermal impedance ZTH. And ZTH is depending on the applied pulse length and duty cycle, and for a duty cycle of 1 and large pulse length TP, ZTH would be the RTH value. And this normally is also plotted in the data sheet. This is the ZTH junction to ambient graph. On the right side of this graph, you see the case for duty cycle equals 1, as I mentioned, and a large pulse length. Then we have ZTH equals RTH. And as soon as we vary either the duty cycle or the pulse length, this graph is spread out, and we have different kinds of values for this thermal impedance ZTH. For more details about ZTH, I would like to refer to the our diode application handbook, where you can find more details about the ZTH. With this, I would like to hand over to Nima, and Nima will explain thermal benchmarking, especially comparing SMx versus CFP.
Thank you, Hoan. So in the first two webinars, we focused on choosing the diode based on the electrical requirements of the application. Now the focus shifts to the thermal considerations the application comes with. And with that, the focus will now be on the thermal parameters of the devices which are displayed next to the circle here. So as just has been introduced, we have for DC conditions, so constant power flow, we have the RTH. For transient events, for example, startups, we have high current pulses through the system. Then you take the thermal impedance. And of course, it's also important how much ambient temperature is present when the application is operated. So how much headroom we have to the maximal junction temperature. And of course, last but not least, the total power dissipation. So how much device can our device handle. What we will see in the course that this value can be altered when the thermal stack is changed. So how these device-specific diode parameters and PCB layout affect the application, this is the question we will try to answer in this section. So our approach was to start with 4 different layouts we specifically designed for this to map typical applications to PCB layouts. We have 2 two-layer PCB layouts, which are displayed in the top, and we have 2 4-layer PCB layouts. All have the same copper thickness of 35 microns, and on the bottom side, a square of the same size for all the boards, where the solder mask is released. So, and we start with the top left design. Sorry for that. Here we have the standard footprint, and on each of the on each designs we tested 3 60-volt 1 amp Schottky diodes with comparable die size in CFP2 HP package, in the CFP3 package, and in SMA. And the standard footprint, or as you can find it in our datasheet, the recommended footprint, always delivers the poorest thermal performance, because there is no space on the PCB to dissipate, to sink the heat into. These types of application, this type of PCB layout is often found in auxiliary applications like for snubber circuits or for the bootstrap circuit. Now, for the second 2-layer design, we have an extended heatsink of 1 square centimeter for the cathode tub. This is a typical layout which can be found in reverse polarity protection applications. As a side note, it should be said that the previous layout, so the standard footprint and the 1 square centimeter heatsink, are the most common layout conditions when we as an exterior specify RTH and PTOT values, where the copper thickness may vary from the 35 micrometers. Now, if we improve the or if we increase the layers in the PCB, we come to the 4 layers, and here we have extended the heatsink of the cathode tub a little bit to fit a row of vertical of vias, three rows of vias, which connect the cathode tub to the same to a copper plane on the bottom side of same size. This type of design is often prominent when the diode is used in freewheeling and buck converters, because here the cathode is connected to the switching node, and you have to find the perfect trade-off between the thermal performance, the small commutation loop, and electromagnetic compatibility. This is a little bit different for our last design. Here we have extended the heatsink further to fit 3 rows of vertical interconnects to the bottom side, and here the whole bottom side is then connected to the same potential. This can, for example, be the cathode connection of a boost diode in a boost converter, because here the cathode is connected to the output potential. So before showing you the results of how the 3 devices perform on each of the layouts, let's have a look on the thermal stack itself and how we need to improve it, that we can actually measure the thermal performance. For that, let's jump back to the cross section, which has already been introduced. And to make it a little bit more clear, for example, we take as an example the PMAC 60 volt 1 amp in CFP2 HP package. And as you can see here, if we follow the path from the die to the solder point, all these thermal resistances are related to the package. And the thermal resistance for the CFP2 HP package from junction to solder point is 6 Kelvin per watt. Now, if we want to measure the thermal performance, we will always measure the PCB thermal to ambient resistors with this. And if you compare the values, RTH junction to ambient, thermal resistance for standard footprint is 230 Kelvin per watt. So whenever you measure a device on standard footprint on a PCB, you will always characterize your PCB to ambient. So what we need to do is we need to improve our thermal stack, or in other words, minimize the RTH PCB to ambient thermal resistance. And one method to do that is to introduce a heatsink. And this heatsink is kept at 25 degrees C. The PCB is connected to the heatsink by a thermal interface material to ensure good conductivity. And this is also the reason why we removed the solder mask on the bottom side to also ensure a good thermal conductivity between the PCB and the thermal interface material. Now we have introduced a thermal resistance heatsink to ambient, which is way smaller than the RTH PCB to ambient. This will allow us to move the RTH junction to ambient closer to the RTH junction to solder point. And on the top right side, you can see the measurement setup. So we have a water-cooled heatsink where the PCB is screwed to, and the diode is biased in forward direction. But what you also can see that we have no additional measures in terms of thermocouple or infrared camera to measure the temperature of the junction. So in order to measure the temperature of the junction, let's take another step in between before we come to the results. And for that, we look at the schematic of our test setup. So as I mentioned, the diode is biased in forward direction, and we supply the diode with a constant current and measure simultaneously the VF. The diode under test itself is pre-characterized, and the IV curves are recorded over temperature. Again, we take the IV curves for our 60 volt 1 amp Schottky diode in CFP 2 HP, and the IV curves show the temperature dependency of VF for constant current if you draw a horizontal line at a specific current. And when you now collect all the intersections and plot the VF values over the junction temperature, you get a temperature dependent curve for 2 amps, for a constant current of 2 amps for VF. And this we have done for all the currents, so example also for 4 ampere. And since we know which current we are going to supply to the diode, we can use the diode under test itself as a temperature sensor. And this is why we also can speak here of a virtual junction temperature. So now that we have fully enlightened the background of the measurement, we can now look at the results. So here, please excuse the busy graph, but I will guide you through it. Here you can see on the y-axis the total power dissipation for a junction temperature of 175 degrees C, which is the maximum junction temperature for our devices. It's given in watts. And on the y-axis, you can see all the different, the 4 different PCB layouts, which I have introduced in the beginning. For each PCB layout, we have grouped the total power dissipations for our 3 diodes under test. So in petrol, we have the SMA, in violet, we have the CFP 2 HP, and in orange, we have the CFP 3. And let's start with the standard footprint 2-layer design. And it's no surprise that here the biggest package will have the highest power, total power dissipation, and the smallest the lowest. But three things are remarkable for this graph. We can see here that for an improved PCB design, the distance between the different packages is getting smaller and smaller. The second remarkable thing is that first the smallest package overtakes the CFP3 package for the first 4-layer design, and even overtakes the big SMA package for the last 4-layer design. This again emphasizes that a good thermal design or a good PCB layout will always give you an enhanced pitot value. And one thing which is not quite obvious, but if you look closely at the difference of the two last points for the 4-layer PCBs for each package, you can see that the difference gets smaller for the SMA package and the CFP3 package, but not for the CFP2 HP package. This means we have a kind of saturating for SMA and CFP3, which means that we are pretty at the end of their thermal performance, but not for the CFP2 HP. Here we can see that if we would further improve the PCB, that we still are able to draw more power out of it. In the table on the right-hand side, we use the pitot values, which you can see, which we have just spoken about on the graph. We use them to calculate the new RTH junction to ambient for the different thermal stacks. Now, if you remember, for standard footprint 2-layer, the thermal resistance we specified in the datasheet in free air was 230 Kelvin per watt. Just by presenting an active cooling, we reduced the value from 230 to 63 Kelvin per watt. And if we additionally improve the PCB to 4 layers with vias connected to the bottom side, we can reduce this RTH junction to ambient value by half. Now, there's also a different point of view to look at this. If you have a high packing density on your PCB, you want to ensure that the power density of the package for the die you choose is quite high. And this is what we are going to show on the next slide. Here, we have the surface power density. So we divided the total power dissipation by the occupied area, which delivers us the surface power density. And the occupied area is the whole you can see in the top right corner. And here again, it's the two things which are obvious. The CFP technology has superior surface power density compared to the SMA. And you also can see here the kind of saturation I just mentioned in the previous slide. Another remarkable thing is that the CFP2 HP can provide enhanced surface power density of above 1 watt per square millimeter, which is quite high. At the end, I would like to show a slide or graph where we, on the right-hand side, for the last layout, for the 4-layer with the extended heatsink, and here we have plotted pitot in watts against the junction temperature for all the packages Ole has introduced in the beginning. On the bottom side, you can see what kind of electrical parameters they are. And I just want to highlight two things. First of all, we can perfectly see here the linear relationship between the p-tot and the T-junction. And we can see here also that the CFP technology, which has a heatsink, offers on par or better performance than its SMx counterpart. And with that, I would like to hand over back to Ole, who will show you the results for the board level reliability.
Right. Yeah. As we've seen that we could achieve on par or better thermal performance, we also wanted to cover the topic how the CFP packages behave with respect to reliability. And maybe some of our customers do have a long track record of SMx packages as they're using these parts for several years. But in case you don't have these experiences with CFP packages, we would like to share our insights on the board level reliability testing. So yeah, in general, these tests go beyond our standard ACQ qualification, and it's a method to evaluate the reliability of a component on a PCB. And for that, we have investigated the following products in the SMA, SMB, SMC, as well as the CFP5 and 15B. And on the right, you can see the board level reliability tests which we have performed. So the first one is the PCB bending test according to the IC 221. The second one is the shock or the drop test according to the JEDEC standard. And the last one is the temperature cycling test. And now in the following, I would like to guide you through the tests and explain the test setup and for sure also the results. So the first one is the bending test, and you can see that 5 pieces are mounted to the center of a PCB. And to further illustrate that, I'm going to show a short video. So the PCB is placed upside down on this holding mechanism, and a stamp bends the PCB with a constant speed of 1 millimeter per second. And the bending depth is then increased by 1 millimeter per bending cycle. And we have stopped that at a maximum bending depth of 8 millimeters. And here you can see the results for all the products. During the whole test cycle, we are performing electrical tests to monitor the performance and if we observe any fails or not. And up to a bending depth of 8 millimeters, we did not see a single fail. That leads us to the conclusion that the SMA BC as well as the CFP packages do withstand the bending test without any fail. Now coming to the drop test. This is being executed according to the JEDEC standard as mentioned, and the PCB is screwed to a so-called drop table. This is what you can see here again in the video, and this is being dropped from a specific height to achieve a peak acceleration of up to 1500 G. And the stop criteria for this test is that either 80% of the devices fail or a minimum of at least 1000 cycles has to be passed. And the results also showed that we stopped the test after achieving more than 1000 drops. And again, here all the packages did withstand this drop test. Now coming to the last one, the temperature cycling test. Here you can see that we have 15 devices per PCB, and the products are exposed to the depicted temperature profile on the right. So one cycle is 50 minutes, and we have a temperature ramp of 15 Kelvin per minute. So the maximum temperature here is 125 degrees C, and the minimum temperature is -40 degrees C. And we have started the tests a long while ago, and the tests are still running. But At this point in time, we have already passed over 3,000 temperature cycles, and I'm pretty sure that these products will even survive much more temperature cycles. So let's see. We simply keep the tests running, and maybe we're going to stop them at 6,000 or 8,000 cycles. So all that leads us to the conclusion that all the tested products are highly reliable, and we did withstand all the BLR tests which have been here performed. And with that, I would like to summarize today's session. So first of all, we've seen that the CFP packages enable huge PCB space saving potential. So if we take the SMA as a basis, we can save up to 75% of board space if we change the package towards the CFP2 HP. Then we have learned that the RTH junction to solder point is a device-specific parameter, whereas the RTH junction ambient relies also on the PCB layout. Then Nima explained that we could achieve the same PTOT or even better PTOT performance if we have a well-conducting PCB. So yeah, it is super important to have a proper connection and a well-conducting PCB to make use of the RTH advantages of the CFP package. And in the last chapter, I have shown that CFP as well as SMx are very reliable packages. So the last word on the left, you can see the link of the diode application handbook. So if you visit our website, you can download either a free PDF copy or you can order a paper copy. This is being sent to you in case you fill in your contact details. So with that, I would like to open our Q&A session. So please feel free, if you have any questions, type them